Welcome to Topic 10, Part 2 of 2, Dr. H's Artifacts of Import. In video 1, we talked about artifacts of import and not so import in aeronautics. In this video, we're going to talk about those artifacts that are important and not so important and why for astronautics. So instead of aviation, we're going to talk about space. Before we begin, let's look at our questions again. Which aerospace engineerings are important to remember? As I jokingly said, I want you to remember all of them, but not really. But think about which ones set the standard for all that came later or led the path, and which ones pointed down roads not to go. We're definitely going to talk about a couple of these. You're going to see some of the ones that are really famous and common today are left off because while they are the future, they haven't really established the trend, and other things may have preceded them in that, and maybe which ones are overhyped. And there's a big one we're going to talk about in a little bit. So let's kick off with astronautics, with launch vehicles. So we cannot have a discussion about launch vehicles unless we talk about the R-7. It was developed by the Soviet Union under the guidance of Sergei Korolev, and it was designed as an ICBM. That's an intercontinental ballistic missile designed to deliver one thermonuclear warhead. As an ICBM, it was crap. There's no other way to say it. It had to be fueled just before you launched it, because it was a semi-cryogenic. So it uses a synthetic kerosene and liquid oxygen. So obviously the liquid oxygen cannot be stored. And that would take a few hours. It was exposed on a very exposed pad in either Baikonur in Kazakhstan or other cosmodromes and launch sites. And then the infrastructure required was significant, because the original R-7 and actually everything up before the Soyuz 2 had to be pointed in the right direction. It didn't have steering capability like most modern rockets. So all of this made it extremely vulnerable as an ICBM. However, because Soviet nuclear weapons were so massive at the time, it turned out it had a huge amount of payload that it could put into orbit. And as such, it forms the backbone, the originator of the family of the most launched launch vehicles of all time, well over 1,200, and I think we're approaching 1,500 R-7 derivatives have been used as launch vehicles for launches. Success rate is mixed. It's still pretty high considering its age, but this is the epitome of simplicity in design. The original 0 and +1 stage didn't use explosive bolts. In fact, the entire rocket was held to the pad by its own weight, and as the thrust takes up the load, the pad fingers fall apart. Then when the boosters burn out, they naturally fall away. It was only in later derivatives, when they added a second stage, that they added complexity like explosive bolts. As I said before, the engines are lit with giant matches effectively. It is immensely simple, and it is amazingly reliable. If not the most efficient or cost-effective launch vehicle, it's still the basis. Moving on, we have the reliable one. Here is the Delta II. This is the first launch vehicle ever to have 100 consecutive successful launches. Its 100th consecutive successful launch was its last mission. It was the backbone of American NASA science missions, sending probes to Mars and other parts of the solar system. It's a derivative of a US Navy ballistic missile program. So you'll see a lot of these early launch vehicles are derivatives of missile systems. And then they just upgraded over time, but the same basic core arrived. And this forms the basis of the Delta IV expanded evolvable launch vehicle, which is one of the larger launch vehicles and has the ability to put large 25 tons into low Earth orbit and the like. In this design, you see it's got a basic core with a number of strap-on boosters. It's not that it didn't have its failures. It's just that fact that 70 launches in a row, or 100 launches in a row at the end is pretty amazing. It's not going to stand forever. The Atlas V and ultimately the Falcon 9 will probably surpass it in terms of total consecutive successful launches, but it's the first one ever to even get close to that number. So it's the reliable one. The future. So all of you are familiar with Falcon 9 and its ability for the first stage to return to launch site or return to the drone ship after launch. And the first vehicle that actually demonstrated the ability to lift off vertically, fly a distance horizontally, and land as a potential launch vehicle was this. It's called the DCX. It was developed by McDonnell Douglas to answer a call for a single stage orbit, fully reusable launch vehicle. Now we can talk about whether that's a good idea or a bad idea, having a single stage, but everyone else built lifting bodies, basically flying systems like aircraft that took off and landed horizontally. And Douglas, on their own dime, said, you know what, we're going to demonstrate that you can do this purely as a rocket, lifting off like a rocket and landing like a rocket. And it was engineers that cut their teeth on this program that ultimately helped SpaceX and New Blue Origin with their New Shepard, New Glenn program demonstrate and be able to do this. So this is the one, 1990s, an amazing achievement. And it was going to be built into even larger DC Douglas, McDonnell Douglas launch vehicle and the like before the program was canceled. The single staged orbit, Lockheed was awarded the contract. It went nowhere ultimately. And then that's what we have. So this set the stage for the future. The next launch vehicle I'm going to talk about is the one that everybody uses as the warning. This is what not to do. Why would you ever do something like this? So this is the Space Transportation System, more commonly known as the Space Shuttle. And you'll know it's Space Transportation System because every launch was given a number, STS 101, STS 25, all of that. It suffered 2 catastrophic accidents and about 200 and something missions. So, not great. But the big thing about this is it was the most costly launch vehicle ever devised. It was meant to fulfill 2 distinct and different missions. Obvious mission 1 was NASA's goal and need to service the space stations. And at the time it was being designed, that was Skylab. And Skylab was supposed to form a permanent outpost in space that they would add to and all of this. Obviously, there were some issues with the Skylab launch. They lost some of their solar panels. It was a kerfuffle. Space shuttle was delayed. Skylab was not able to stay in orbit because it couldn't be replenished, refueled. It was deorbited, crashed in the Australian outback, and the US got fined for littering. But this is what it was designed for. Its other mission, which is less talked about, one that it never actually flew, was to fly polar launches out of Vandenberg Air Force Base to launch spy satellites. But it wasn't a normal launch. So the space shuttle and NASA would go up, it would stay in orbit for up to 2 weeks, and then come back to Florida. The U.S. Air Force National Reconnaissance Office spy satellite mission, it would do a launch, deploy a satellite, and return to the Earth in less than one orbit. And therefore, it would return to the launch site, back to Vandenberg Air Force Base to make refurbishment and getting it ready for the next flight quicker. And to do that, because in one orbit, the Earth rotates, and it rotates at Vandenberg latitude roughly 1,000 nautical miles. The space shuttle needed to get 1,000 nautical mile cross range. That means it had to be able, on reentry, to fly east-west 1,000 miles. Now, NASA didn't need that capability. But what that means is you have to have a much, much higher lift-to-drag ratio, which means you have much bigger wings. Well, that imposes other constraints. And it was that constraint and that design that ultimately led to the shedding of the foam that broke through the heat shield on the leading edge of the wing that caused the loss of Columbia. We can add to that NASA wanted to do it on the cheap. They didn't want to have liquids. They had very, very advanced space shuttle main engines, and then we had our solid rocket boosters. Now, I was in a meeting years ago with a member of the company that developed the solid rocket boosters, and it's Alliant Tech Systems. It's gone through several ownerships, but back then it was called Morton Thiokol. And he said to me, honestly, and he said the whole group actually, he said, the solid rocket boosters are a nightmare. If we had to recertify those boosters, this was back at the end of the 1990s, based on the rules, it would be worth it for us to ask NASA to pay for the certification and then give NASA as many solid rocket boosters as they could ever have for free. And that's the disaster. So space shuttle, it was meant to be cheap and reusable. The idea was to have 100 missions a year on the 4 orbiters. So 25 missions a year per orbiter. Each SSME was supposed to last between 25 and 100 flights and then be replaced, and it was supposed to be cheap. In the end, we were having 1 to 2 missions a year. Instead of costing $1,000 a pound or less to launch, it was costing even more. The missions were over $1 billion each. You can put 25 tons into orbit, so roughly 50,000 pounds. You can do the math. We're talking a huge amount of money. So we're talking actually over $100,000 a pound in the end. So this was a mistake in many ways. It was what you get, as they say, spacecraft designed by committee. So this is where not to go. The Soviets went to do this, and all of their rocket scientists said it wasn't a good idea. They built Buran. It flew once. Obviously, there were lots of issues. The Soviet Union was bankrupting and collapsing at the time, but it wasn't a particularly successful mission or successful system. And they're still flying Soyuz. So those are launch vehicles. Let's talk about actual spacecraft, the stuff that stays in orbit. So we have obviously the orbiter and the like, but these are more sophisticated systems. Here we have the originals. On the left, you have Sputnik 1, and on the right, you have Vostok 1. So what are these? Well, this is Earth, the first artificial satellite to orbit Earth. And of course, the Soviets put it up in 1957. In 1961, they launched Vostok 1 with Yuri Gagarin. Now, an interesting bit of trivia. Yuri Gagarin was launched into orbit on April 12, 1961. Exactly 20 years later was the launch of the first space shuttle on April 12, 1981. So it's Gagarin's day, Gagarin's start, but in 20 years, we went from this to space shuttle. Space shuttle was now almost 40 years ago, 39 years ago, first launch, 39 and a half years ago. Look where we are. We're back to capsules and the like. But these are the originals. This is what started in terms of spacecraft, what we have today. These are the first probes to go to other places. So this is the Luna probe from the Soviet Union. It was the first artificial probe to go to the moon. And then, of course, we have Apollo. And Apollo was the first human beings, astronauts, to set foot on an extraterrestrial body. They set foot on the moon, and we had several missions with Apollo 11 through Apollo 17 minus Apollo 13, and all the people walked on the moon. There's only a few left and of people that walked on the moon. But this set the stage for what we can do and what our extremes are. Now, to give you an idea, the NASA budget for the lunar system was about 1% of GDP per year in the US. NASA's budget today isn't really any higher in monetary real value, but it's a much smaller percentage of GDP. But that was just the race, and they decided to do it. They did it because it was hard and it showed the capability and the standard. But keep in mind, one of the things about going into space is everybody was afraid we'd use it as weapon systems. And going to the moon, not a really good weapon system, but we can do other things with it. Now, we have here is one of the 6 man-made objects that is either left or will leave the solar system. You have Voyagers 1 and 2, which this is one of, and then the New Horizons spacecraft that went to Pluto, flyby on Pluto, and they will all leave the solar system. Their final stage boost vehicles are also on that trajectory. So both Voyager 1 and Voyager 2 have left the solar system. They passed the heliopause, and we're still getting signals from them occasionally. And this is the epitome. These are the fastest vehicles man has ever built, and they're very slow in the galactic sense. And they have left the solar system, and they were designed as 2 probes to go visit the large outer gas giants. They each took a slightly different path. They went to Jupiter and Saturn and did flybys, and then Uranus and Neptune, and they went out. And the interesting thing is Voyager 1 was launched after Voyager 2, but because of its trajectory, it was going to reach the outer planets first, so they renamed it. And then Voyager 2 ended up, because of its trajectory, leaving the solar system first. But now Voyager 1 has also left the solar system. Said there's only 3 man-made objects that have ever achieved escape velocity from the sun, and the Voyager, New Horizons spacecraft, and their final stage launch vehicles. Okay, what are these satellites? Why do I say your life? These are the satellites, the type of satellite that you probably have the most interaction with. These are communication satellites. We have Telestar 1 on the left was the first one, and this is a modern communication satellite bus. These modern ones are generally placed in geostationary orbit, though we're getting some in lower orbits now where we have like Iridium and the Starlink. Telestar was not, it was a low Earth orbit and you only had brief periods of time. But when you watch live feeds from far away, sporting events or the like, we're using satellite technology. Even a live news broadcast, say from Manchester that's reported in London, is probably done via satellite link. So this is something that's really useful. It's the bit of use of satellites, the one of the uses of satellites that's changed the world. The other really consequential one, of course, is weather satellites, because it's greatly reduced the risk from things like hurricanes and other storms, death tolls, and the like. So we take those communication and weather satellites as probably the two single largest day-to-day things that affect your life. Okay, so that brings us to the end of satellites. I didn't show you the Hubble Space Telescope, which is probably the greatest scientific achievement of the manned space program. We can talk about that some more on Monday. But as a wrap, I've given you a small assortment of important aerospace systems, the ones I think are. It's by no means the totality of it. I've told you why some are important, why they're the standard bearers and set the stage. Gives you ideas of ones that really aren't, you don't want to repeat. We've walked away from, we've tried that, done that, have the t-shirt, we're not going to do it again. And as I said, we can include a lot more. These are time and personal interest, but it gives you a set. It links you back. I would like you again to think back in all of the different things we've talked about, the different topics, how each of these artifacts of import either played a role in us discovering things about it, swept wings, that kind of stuff, or made use of a new technology that came about at the time. And then I want you to think about the failures, because we learn a lot from failures in engineering. While we don't want to fail catastrophically like Challenger or Columbia, it's very good for us to do early failures and understand and learn from them. Remember, a smart man learns from his own mistakes. A wise man learns from the mistakes of others. Be a wise man. I'll see you on Monday, and the next video I'm going to put up will be a video on revision that you can watch at your own leisure. Thank you.